Hello and welcome to video 3 of 3 for chapter 8. Now in this video what I'd like to do is to explore what happens when an electric field passes through a material with a little bit of realism added in. And then I want to talk about how this realization uh, affects not only the energy that's stored in a capacitor, but also the ability of that capacitor to store energy. Now, to start with, what I'd like to do is to think about the standard model of the atom that we're familiar with, where you have a nucleus, which is composed of neutrons and protons, and then you have, going around your nucleus, uh, an electron or so. Now, the proton is positive. Neutrons we know are neutral. So the nucleus is overwhelmingly positive. And in, we know, a neutral atom, you should see the same number of minus charges going around it in the form of electrons as you do the positive charges that you see in the nucleus. So what happens when you take and you run an electric field through an atom? Well, let's pretend this is an electric field. I'm going to call this E naught. This is what's called an external field. Why is it external? It came from the outside. So we know, according to the relationship between force, charge, and the electric field, that positive charges are pushed in the same direction as the electric field. But negative charges are pushed against the field. They're pushed anti-parallel to it. And what that does to an atom is to elongate it. So your atom sort of almost looks like, just to exaggerate it, like a grain of rice. And if you think of this as being the direction of the electric field that's passing through, you're going to have a region that's positive and you're going to have a region that's negative, like this. They've been separated. So what we've done is we've created a dipole moment. But look, electric fields we know point from positive to negative. And what's happened is by elongating this atom, we've created a tiny little electric field called the polarization field that points this way against the direction of the external field that came through. Now you could think of this when you add up its effect over an entire substance, because this isn't just affecting one atom. This would be affecting all the atoms that are in line with the electric field as it goes through. Okay? So what this does is to create what's called an internal field. And as a consequence, when you look at the overall field, you have this external field and the internal field's contribution as well. So if we called the internal field's overall effect as E sub I for internal, then your effective field would be the external field plus, as a vector, whatever the internal field is. Now, this is induced. It wouldn't be there if it wasn't for the presence of this external field. Okay? It wouldn't be there if it wasn't for that. So, one thing you can do is to look at the relationship between the overall field and the field that you put in. Because if you can look at that relationship, that allows you to find a relationship between the field that you put in and this induced or internal field. Okay? So what you do is you think about this. Look at the ratio of, say, the field that you stuck in to the ratio of the field that comes out. Okay, because it's going to be affected by this induced field. And then now let's take a look at this. Now in magnitude they look like this. All right. So what I'm going to do is to write E we'll call this ratio kappa. Okay. So I can write E as E naught in magnitude over kappa. Now what I'm going to do is I'm going to plug that into this equation over here. So that says that E naught over kappa is equal to E naught plus this induced or internal field. So if I look at the relationship between the two, what it says is that the induced field is equal to E naught over kappa minus E naught, or 1 over kappa minus 1 times the field that we put in. So this is the relationship between them. And this right here, this kappa thing, is called the dielectric constant. Now, in truth, any sort of substance that's not a conductor that you pass an electric field through can act this way. And things that act this way we call dielectrics. So this is dielectric. There are lots and lots and lots and lots and lots of examples of dielectrics. I'm going to grab a few here and copy them in just so you can get an idea of what a few of these kappa things might look like. So let me grab this real quick. Let me find my list of dielectrics here. And this is from your book. You can find it here. Give me a second. I'll tell you what page it's on. This would be page 372 in your book, chapter 8. So for a series of these things, just a few of them, a little infinite number of these things. Your dielectric constant kappa varies from vacuum, which would be nothing between the plates of your capacitor, nothing, your field is passing through empty space, if you will, to air, which is more or less a vacuum, to things like Teflon, paraffin, silicon oil, paper, water, sulfuric acid, barium titanate, strontium titanate. Okay. Now, what's interesting to us about this, at least with respect to capacitors, is that you can use the dielectric properties of a material to enhance a capacitor's ability to store energy. And that's because in elongating these atoms, you're sort of adding energy into the mix. Okay? Now, it's actually very easy to get from one to the other. Basically, what we do is we take our capacitance whenever we have a dielectric present. Like, for example, remember the capacitance for parallel plate capacitors looks something like epsilon naught A over D. And what we do is we just insert a kappa in front. So our new capacitance would equal to kappa epsilon naught A over D. So for example, the act of putting water inside or in between the plates of your capacitor increases its ability to store energy by a factor of 80. Now that's fantastic. So that allows you to get away with much smaller capacitors that can store much more energy. But there's a caveat. And the caveat is the following. You now have a real substance that sits between the plates of your capacitor. And as a consequence, it is possible to have enough electric field present that you pull your atoms or your molecules or whatever it is that you're using as your dipole apart. And when that happens, what that does is to turn your dielectric into a conductor. Now, if you think about the way a capacitor works, a simple parallel plate one, you have a region of positive charge, you have a region of negative charge. And the idea is there's nothing in between. If you were, for example, to attach a wire from here to here, then the negatives and the positives could flow freely, and this capacitor would very quickly lose its charge as the negatives and the positives sort of move to rejoin each other. Actually, it's just the negatives, and we know that. All right. So when your capacitor, when your dielectric breaks down, when you get to a voltage, or not a voltage rather, but an electric field strength that's such that you can pull these things apart and your dielectric becomes conducting, then your capacitor discharges, and often it discharges incredibly violently. It explodes or burns up. So that's called dielectric breakdown. And what you'll see here is that for each one of these substances within reason, there is what's called a dielectric strength. And that dielectric strength basically tells you what the strongest electric field is that you can have going through this substance before you rend it apart and it becomes conducting. Now, just with a simple example, let's pretend you have the following circuit. You have a voltage source. You have a capacitor that has vacuum between the plates. Your battery here is 12 volts. And we'll pretend that your capacitor is 4 microfarads. Now what I'd like to find is the following. Stored charge. And then I'd like to find the stored charge for the same capacitor, but with mica in between the plates. Now, if you look up mica, mica has a dielectric constant of 6.0. If you look at its dielectric strength, mica breaks down at around 118 times 10 to the 6 volts per meter for the electric field. And at 12 volts, there's no way you're going to get that strength of an electric field between these plates, at least not within reason. So our capacitance before it's been altered is 4 microfarads. When you take and you put your dielectric there, I'm going to call this C effective. It's kappa times C, which is 6 times 4, which would be 24 microfarads. So it's substantially increased the capacitance. So Q is equal to C times V. For the vacuum one, RQ is going to be 4 microfarads, which is 4 times 10 to the minus 6 farads, times V, which is 12 volts. And if you do that calculation, 4.8 times 10 to the minus fifth. So that's how many coulombs are stored in the one that doesn't have a dielectric. Now, when you do the dielectric, things change. .88 times 10 to the minus fourth. So as you can see, you can store a tremendous amount of charge between the plates with the addition of this dielectric, assuming that you don't violate the strength of the electric field. When you violate the strength of that electric field, or that maximum, if you will, then things break down and you have some serious issues. So let's do another example. This is a little more practical. I want you to think about a nimbus cloud. It's a storm cloud that sits above the ground. So here it is right here. Now, the bottom part of a nimbus cloud is negative. It's a negative charge. That's because layers of the atmosphere within the cloud and the dust particles and stuff that actually form the cloud or give you sort of a substrate for the water to form around to create raindrops, it actually creates a lot of static. So you have a region of positive that sits at the top, and then you have a region of negative that sits at the bottom, the sum of which gives you 0. Now, so nimbus clouds usually sit about 2 kilometers above the ground. I'm going to call this D. This is 2 kilometers or 2,000 meters. We're going to pretend that the area of this nimbus cloud is 1 square kilometer. That is, 1,000 meters by 1,000 meters, or 1 times 10 to the 6 meters squared. That's its area. And it's air that sits between the cloud and the ground. And if you look at the dielectric constant for air, it's for all intents and purposes 1. We're just going to call it 1. But it does have a dielectric strength. Its dielectric electric field strength ends up being about 3.0 times 10 to the 6 volts per meter. Okay. So one thing I'd like to find is the stored charge. Now, I'd also like to find the potential difference. But I'd like to find both of these right at the point to where you have a lightning strike. Now, why is that? Well, all right. When you see lightning crash to the ground, what's happened is that the electric field between the cloud and the ground has hit this. When it gets to this point, the air breaks down and turns into a conductor. And then the electrical charge that sits here at the base of this cloud just follows the path down. So what you want to do is to find what the difference in voltage would be between the top and the bottom, such that this breaks down with a distance of 2 kilometers between the cloud and the ground. So if you just think of this in terms of magnitude, the difference in voltage, or just V, would be the electric field times the distance. So 3.0 times 10 to the 6 volts per meter with 2,000 meters. So 3 times 2 is 6. You have 6 here, a 3 here. 6.0 times 10 to the 9th volts. That's a lot of potential difference between here and here. Now, how much charge would be stored in this? Well, we're going to treat this as though it's a parallel plate capacitor, because you have the ground, you have the cloud. We're going to assume the cloud is parallel to the ground. You know what the area is. That's going to be the same area more or less on the ground that has the charge that's being induced in it. So here our capacitance would be kappa epsilon naught A over D. But really kappa is just 1. So epsilon naught is 8.85 times 10 to the minus 12th Coulomb squared per Newton meter squared. The area here is 1 times 10 to the 6 square meters. And then we're dividing it by the distance between, which is 2,000 meters. So our capacitance here is going to be 8.85 times 10 to the minus 12th times 1 times 10 to the 6. And then divided by 2,000. So that's 4.425 times 10 to the minus 9th farads. So that's the capacitance. Now, what about the stored charge? This is going to be the charge that's going to end up hitting the ground. Well, Q is equal to C times V. C is 4.425 times 10 to the minus 9th farads. V is 6.0 times 10 to the 9th volts. Wow. So it's 4.425 times 6 is what you get. So that's 26.55 coulombs. That's a tremendous amount of charge. That is a ridiculous amount of charge. And it's spread all over the surface of this bottom of the cloud. Okay? So, if we assume 1 sig fig, because we are sort of estimating this, this would be about 30 coulombs of charge. Excuse me. So, this is how much charge ends up making its way to the ground, which is the reason why if you get between, the sky and a lightning bolt on the ground, you're in for a bad day. Now, that said, let's talk about the electric field. All right, so now let's talk about where the energy sits. Specifically, I want to think about just the simplest example of the capacitor that we can deal with, and that's the parallel plate capacitor. We know, for example, that with a parallel plate capacitor, the capacitance is a geometry game. There may be a dielectric, so you may have a K there, or kappa. But it's going to be epsilon naught A over D, where, A is the area of, one of the sides of the plates, and D is, the distance between, right? Now, we know, for example, that the amount of charge that would be stored on this thing would be equal to Q is equal to C times V. Now, but we also know that V itself is an energy. It's related to energy. V is easier to deal with. But the relationship between V and if you will, U, the potential energy, the stored energy, is this. Okay, that comes from like chapter 7, I believe, 6. Chapter 7. So I'd like to look at this equation and basically take the differential of it, noting the fact that the geometry of our capacitor doesn't change, so it's a constant. So if I do that, dq is going to equal to c times dv. Now, what I'd like to do is to take my dv right here and plug in this so I can relate it to potential energy. So now if I solve for du, I have 1 over c q dq. So the act of charging this is storing energy within the capacitor. So I'm going to integrate both sides. When I integrate the left-hand side, that's going to give me the total stored energy. I am going to start, I'm going to bring the c out because it's constant, from a charge of 0 and take it all the way up to whatever its maximum charge is going to be. Q dq. Now, when I do this integral, this is just 1/2 q squared. Evaluated from 0 to q, which is just, 1 over 2c q squared. So, there are a couple different ways you can write this. For example, if I ask you how much energy is stored within this capacitor and I tell you, or you're able to find out how much charge, it's just 1 over 2c times q squared. Or I can use the fact that q is equal to c times v and plug that in. And when I do that, I get 1/2 cv squared. And this is the more common way that you see this written. Now, to be clear, this is the total stored energy. Now, one of the things, though, that's more convenient to talk about instead of total stored energy is something called energy density, which is something that I'm going to get into right now. So what I'd like to do is to pull in from this version of our stored energy this definition of capacitance, but also the relationship between voltage and the electric field. Now we're going to assume this thing has been charged up, the voltage is constant, and as a consequence the electric field is constant. And we know that V is equal to minus, for constant electric fields, E dotted with dr. Now ultimately when I do this, E and dr are going to be parallel to each other, but I'm squaring things when I plug this in. If I call the distance between the plates d, the dr, the delta r, becomes just d. And when I plug it in here, it's going to become positive. So the capacitance looks like kappa epsilon naught A over D. The voltage looks like E times D squared. Now, if I look here, I see there's 2 D's here. There's 1 D here. This is going to kill one of these things off. You have a kappa. You have an epsilon naught. You have an A times a D. I want to put those in parentheses for a moment. That's because you lose one of these D's to the one that's in the denominator. And then you have the electric field squared. Okay. Now, A is the area of a plate. D is the distance between. So A times D would be the volume that sits in here. That's volume. So if I were to divide both sides by this, what I would then get would be something called energy density. It's little lowercase u with little. This is to make sure it's clear. It's lowercase, right? So this right here would be the total energy density that sits between the plates, and it is 1/2 kappa epsilon naught times the electric field squared. Now look, this only depends upon the electric field, really. If you take the dielectric out from between the plates, you don't have any places where you can hide some electric field, then kappa is equal to 1. So what this tells us is that the energy that sits between these plates is stored inside the electric field. Now, kappa times epsilon naught is often just referred to as epsilon. This is just called the permittivity. Not the permittivity of free space, because it potentially could not be free space. So our energy density is just 1/2 epsilon times E squared. So that said, let's use this over here. Now I'd like to ask the following question. How much energy is stored in the region that sits between the cloud and the ground? Now, the energy density is 1/2 epsilon times E squared. This is more or less just a vacuum. It's air. 1/2 times 8.85 times 10 to the minus 12th coulomb squared per Newton meter squared. The electric field is this right here, 3 times 10 to the 6 volts per meter. You got to square that. When you square this, incidentally, this is going to become 9 times 10 to the 12th. There's a 12 here. They're going to kill each other off. Excuse me. Let me 0.5 times 8.85 times 9. I see about 39.825 joules per cubic meter. So inside the electric field, one approximately 3 foot by approximately 3 foot by approximately 3 foot cube of air is going to have roughly about 40 joules in it. So, what about the total amount of energy that's there? Well, if you take a look, you have volume. You have an area at the top, and then you have a distance. So if I want to know what the total energy is, I take the energy density and multiply it by the volume. The area here, 1 times 10 to the 6 square meters. The distance between the plates, 2,000 meters. So when I do this, (7.965) times 10 to the 10th joules, or about 8 times 10 to the 10th joules, which is a lot of energy that's sitting there in that electric field. Again, a pretty good argument as to why you probably shouldn't play golf in the middle of a thunderstorm. So, that's it for this chapter, and I will see you in the next chapter when we start talking about things like current and resistance.